And we had some dielectric in there, and we removed the dielectric. And somebody had asked the question, what happens if you're adding a dielectric? And I thought, that's a good question, and you guys were going to think about it. So these guys have told me the answer. Anybody over here got a solution? You forgot. Okay, so let's charge this up. So we've got a certain charge on it. We know Q equals CV. We know energy is a half CV squared. But the simple way to think about how this one works, remember, I guess with the previous one we argued that if we had the dielectric in here, it became slightly polarized, so the top became slightly negative, the bottom became slightly positive. If we try and pull this out, there's an attractive force at the top, an attractive force at the bottom. The dielectric wants to stay between the plates of the capacitor, and we have to do work on the system. So if we go back to first principles, when we looked at energy and potential, if we do work on the system, what do we do to potential energy? Increase it. So if I work to lift up the bit of chalk, I increase the potential energy. So if I pull this dielectric out, I do work, so I increase the potential energy. The second half of the problem is if the dielectric is outside, well, nothing happens initially because parallel field lines. But as soon as that dielectric gets into the field line, we move it a little bit further in, what happens? The dielectric begins to polarize, so the top becomes slightly negative and the bottom becomes slightly positive. So there's now an attractive force at the top and at the bottom, and that will act to pull the dielectric in. So as soon as the dielectric gets to the capacitor, if you let it go, it'll be pulled into the capacitor. So in that case, which force is doing the work? The internal force. The force of the electric field is doing the work, sucking it in. If internal forces do work, the potential energy goes down. So the energy stored in the capacitor goes down. So you can play around with those equations and you can prove it mathematically as well. That basically the trick is that Q is conserved. Q doesn't change, but the capacitance is changing. You don't know what the voltage is doing. But you know the capacitance is changing because we define capacitance as C epsilon naught K dielectric constant and some Curly function. This depends on geometry, depending what shape. Could be area of plates and separation. Okay, so I guess we're rolling now, so we can start a new topic. Today I want to talk about magnetic fields. So we've done the first part of the course is all electrostatics. We've talked about charges. We've talked about the electric fields that they produce. We've talked about potential. We introduced Gauss's law and capacitors. So today I want to talk about another type of field, the magnetic field. And essentially you can get magnetic fields two ways. You can get permanent magnets, which you may have home, that stick to the fridge with notes on them. So that's clearly a piece of material sticking to a piece of metal or maybe another magnet. So there's some material effect going on there. But you can also get a thing called an electromagnet, which is basically when you apply a current through a wire, you can generate a magnetic field when the current is flowing, and that magnetic field can be used. And I think the book's got an example of a scrapyard where they're picking up pieces of metal and moving them around with some huge electromagnet. So it's a way of actually creating a magnetic field with a flowing current. So both are very similar. We could argue that they're indeed the same type of effect. If we say that the electromagnet, if we've got a current flowing through a wire, that is just a flow of charge. So it's a moving charge. So if we've got a moving charge, maybe that gives us this magnetic field. And we could argue that that might work on the atomic level as well. If we take, perhaps, look at the magnet close to, we could see, well, it's maybe got an atom, and it's got an electron that's circulating around that atom. So a moving electron is current. So even an electron moving around an atom, we could model as a very, very small current. If there's a small current that creates a magnetic field, well, maybe it creates a magnetic field around that atom. And if all the atoms were lined up in the same direction, you could imagine all the little bits of magnetic field add up and give you a macroscopic magnetic field. and hence a magnet that sticks to the fridge door. We won't talk so much about materials and magnetic materials. I guess you must come across that later in your careers. We'll just talk about magnetic fields in this course in terms of moving charge. We'll talk about magnetic fields being created by moving charge, the same way as electric fields were created by static charges. And we'll make some definitions about forces on charges due to magnetic fields. So we kind of start with a historical perspective. So let's just remind ourselves it's magnetic fields. And you recall first week that we met, we said that the force due to the electric field, and we'll put a subscript E here, or the electric field rather, it's just due to the force due to the electric over the charge. So we came up with this concept of charge. So we said we had a force due to the presence of a charge. We need another charge to measure this, so we need two charges to repel each other, and we defined electric field as basically the force on a test charge, which is essentially what this is. So we could define magnetic field in a similar way. We could say it's some force, which we'll call subscript B, now to differentiate from electrical to magnetic. We're still going to use the concept of charge, so it still depends on charge, but this time the charge is going to have to be moving. So that we're going to define a moving charge. So we define a velocity. I will just put down speed at the moment. So in a similar way, we know this is a vector and this is a vector. This is a vector because this is a vector. Velocity is also a vector because it's got direction. So the situation gets a little more complicated because our charge isn't static, it isn't in one place. Magnetic fields and forces produced depend on relative direction as well. So here I've just taken one particular example and said, well, we could call this relatively speed. But if I take this term here up to this side, and I recognize that this is going to be a vector, I'm going to have a vector multiplied by a vector equaling a vector. So what type of interaction is that called? Cross product. We talked about it in first lecture. So more formally or more exactly, So more formally, we say that the force, which is a vector, and we'll put a B because it's going to be due to the magnetic field, is equal to the charge multiplied by the velocity, which is a vector. Velocity has to be a vector because you could be going in one direction along the 401 at some reasonable speed, or you could be going very slowly in the other direction. So velocity is a direction. Speed is the magnitude of that. And that's going to be crossed between this new field, this magnetic field. So this is a more formal definition. So this is our equivalent of, I guess, almost Coulomb's law type of definition. So the force depends on the velocity, depends on the magnetic field. And we know from our discussions in lecture 1 that this is really Q, V, B, sine, let's say phi. And phi is the angle between the vectors V and B. So phi angle between V and B. Okay, so this is what I mean by a vector product or a cross product. So what does this mean? Because equations are just, they're tools to help us understand the concept. So what's the concept behind this? The concept says that if I've got a moving charge In a magnetic field, both the direction of movement and the magnetic field have two different directions. There'll be a force created on that moving charge. What do I know about that force? Well, the faster the charge is moving, the bigger the force is going to be. The bigger the charge, bigger the force. And the bigger the electric field, the bigger the force. So I know in terms of magnitude that increasing B, V, or Q are all going to increase the value of F. That's clear from this equation or the one underneath. The other thing is, well, what's the direction, relative directions? Because we've got two vectors here and we've got some angle between them. So the way you think about these cross products are, if I take two lines or two vectors, or two pens, I can always place them in any place in three-dimensional space and they'll always define a plane. Okay? So if you take two lines that touch at one end and move them in any angle, you can always define a plane. So the vectors V and B define a plane. So this is the geometrical argument. The vector F is at right angles to that plane. So Q and B have to be, V and B have to be in this plane. The force is going to be at right angles. But you say there's two forces, there's two at right angles. Force could be up or it could be down. Which one do I choose? Well, convention says that we use a positive test charge, the way we used a positive test charge for the electric field, and we say that the force would be the force on that positive charge. And that tells us we're going to use a right-handed rule. So you need to get your right hand out. So basically, the simple rule I remember is first finger is the first term in the cross product. In our case, it's QV. So this is QV. Next finger is B. And the final thumb is the direction of the force. So we live in a right-handed world. The book has now got a new, can't speak on a Friday. The book has some other definition, which is a plane, you're moving your hand from QV onto B, and gives, but it's essentially the same thing if you play around with the two definitions. So if I've got a charge moving in one direction, a magnetic field in another direction, I'll get a force at right angles. So things to know, F is always at right angles to the plane by V and B. So V and B define a plane, the force is always at right angles. We want to say a few words about this thing, because we know units for this, this and this, but we want units for B. So we'll use that later on. So just in terms of continuing definitions, B has units of, do you know the units of magnetic field? Tesla. The electric car maker. So easy to remember. So it's 1 Tesla, or 1T. And from the equation we previously had up, you can figure that out in other SI units. Clearly it's going to be force over charge times velocity. So Newton coulombs meters per second is 1 Tesla. A definition that we'd previously written up. Just for completeness, there's another unit. You'll see 1 Tesla is also 1 or 10 to the 4 Gauss. So Gauss, who came up with Gauss's law, also worked on magnetic fields, and there's a definition of magnetic field in terms of Gauss, an older unit, but you'll see it now and again in some textbooks. You'll see people use Gauss. Questions? is the unit Gauss? Oh, it's a measure of, it's just one Gauss. I think they use capital G. Subdividing it into here, it probably is imperial type units, meters, not meters, yards or feet or something. But it'll have the same form. It's still essentially a force, a charge, and a speed. So it's just a scaled version of this. So it's defined with a different set of basic standards. So it's not different in terms of, I'm not saying one, this is 1 degree temperature and this is 1 meter length. They're still both measuring the same thing. So they both essentially have the same units, but you'll see different units, MKS, SI units, and different things that date back when people use different measurements and systems. So Canada, we use a metric system. The UK still has some imperial systems. Distance on the roads is still in miles. In the US, it's imperial systems. So you'll see there are a number of different definitions. So it's a conversion to a different definition. Other questions? Okay. So let's consider an example. I'm going to draw a 3D axis system. And I'm going to have an x-axis, y-axis, and a z-axis or z-axis in this direction. I'm going to take a positive charge, locate it at the center here. So this is a positive charge. It's going to have a velocity along the negative x-axis, so its velocity component is this way. V is that direction. It's going to be propagating through a magnetic field. Which is pointing downwards along the negative y-axis. Which direction is the force in? You can talk to your neighbor. Wake them up if they're sleeping. So this is QV cross B, so right-handed rule. Positive charge moving in one direction through a uniform magnetic field pointing in the other 90 degrees. See, I know if you're thinking about this because you're doing this. And it's the same in the exam when you're doing the tests. I know when you're doing this question because you've got the fingers out. So V, first finger, is along this direction. B, next finger is down. So, yeah, so it's moving this way. Magnetic field is this way. That defines the plane, which is the XY plane. So it has to be in the Z plane, and we use the right-handed rule to say it's out along the positive Z direction. Okay? So force would be in this direction. Okay? Same thing again, X, Y, Z axis. This time I'm going to have a negative charge. So I take an electron this time, not a positive charge. And it's going to move down the negative y-axis. So it's moving this way with a certain velocity. The magnetic field is uniform and all pointing this way along the Z negative axis. Which way is the force? There's a subtlety here because charge has changed. Okay. Any shout outs? Negative x. Anybody else? Anybody disagree? How do we solve this one? Well, we can still use the right-hand rule, but we remember the right-hand rule is for positive charges. So I could still say that V is down, B is into the board, so that would indicate a force along positive x if it was a positive charge. But since it's a negative charge, the force goes in the opposite sense, so that would be along this axis. Or you can label this one positive, and you can do the same thing with this one. For negative charge, if I got V down this way, B is now into the board, so force would be that way. So your left hand works for negative charge, right hand for positive. Or use one hand, but remember to invert the charge. So the force in this one would be along this axis. Okay, now you're experts. What about this one? B is along the plus y-axis, V is along the negative y-axis. We've done BV, integrals of d dot s, move charges through fields. Anything? Shush. You've answered two. I'll ask the back of the room this time. Anyone? Was that a number or 0? Right. Okay, so there QV is at 180 degrees to B. So we know in a cross product, we have a sine of the angle between them. The angle between them is 180. Sine of 180 is 0, so in this case, there's no force. So F equals 0 in this case. So those are some examples where we're moving orthogonally. Of course, you have an expression. This is all F equals QV cross B, where these are all vectors. Some trivial examples along different directions. But essentially, this works with any angle. All I need to remember is this is sine phi in here. So I need to know the angle between the vectors. Then I can work out the relative contributions. Questions? It's the toughest thing that you learn this. Well, one of them. That must be a question. No? Okay. So with electric fields, we defined electric field lines as a way of visualizing what the force on a test charge would look like. We can do the same thing with, sorry, question.
So, you know how like the magnetic field is force divided by magnitude of velocity?
Mm-hmm.
How do you use that to find speed? I mean, sorry, find the direction of the magnetic field.
Yeah, okay, I started with B equals force over QV. So we did this as a discussion. The right-handed rule still works here. Clearly, if I expand this, this is coming from F equals QVB. So here I'm assuming already that I've got right angles, so the sine theta has, I've got right angles, so sine theta is 1 in this. So this is just sort of illustrative. I guess more formally we should say F is QVB sine, and I think we're using phi. So we should really have a QV sine phi underneath if we're being more consistent with it. And we want to work out different directions. Because you're right, it does depend on the relative direction of B and V, and if they're parallel or at 180 degrees, there's no force. So that would be a more correct definition. So it was really just to make the analogy between electric and magnetic fields. So the one to remember is this. Everything else falls out of that equation. Okay, so with electric charge, we came up with electric field lines. And we remember they start on a positive charge, end on a negative charge. It's the force on a test charge. With magnetic field lines, we don't have a north pole or a south pole, which are equivalent of positive and negative charges. North and south poles always come in pairs. So if I take a magnet, bar magnet, or any type of magnet, I'm going to have a north pole and a south pole. If I cut the magnet in half, I'm just going to have two magnets, each with a north pole and each with a south pole. There's always going to be an orthogonal end. So I can't just have a single north pole or a single south pole. So magnetic fields are slightly different in that sense. But we can define magnetic field lines, and basically they start on the north pole. In this case, would exit, and they end on a south pole. So they come out of the north pole and curve back around into the south pole. And you can draw a bunch of these field lines. One along the axis might go to infinity, one here may arrive from infinity, and then more field lines out here. But the same type of argument, the electric field lines, when they were close together, we said that was a big electric field. Same argument happens here. When the field lines are close together, we get big magnetic field. So for example, in this region and this region, we're going to have a much bigger magnetic field than perhaps out at the edges. So the magnetic field can be mimicked or described in space using these magnetic field lines. So these things here are magnetic field lines. And they start on a north pole and end on a south pole. So start on the north pole and they end on the south pole. And regardless of the shape of the magnet, whether it's an electromagnet, which we generate from having a current flowing through some wires or coils or whatever, or a horseshoe magnet or any other shape of magnet, we can still define a north pole, south pole. Magnetic field still comes out of the north pole, ends on the south pole. It just allows us to shape the field in space. There's one exception though, and that's the Earth's magnetic field. So the Earth has got a north pole and it has got a south pole. But when you measure the north pole of the Earth, it really is a south pole. If you could look at the magnetic field lines, they go into the top and they come out of the bottom. Why would that be? Another historical artifact of what we do. How do people navigate in old days in a ship? What did they have? Compass. So a compass has a north pole on it. So when you're in the lab doing experiments and defining lines, this is your north pole. What does the north pole point to? South pole. So just an interesting definition. The north pole in terms of field lines is inverted. Because people see it in geological times, the poles of the Earth invert periodically over millions of years. So, but within humanity's lifetime and navigation, it's been a south pole. But the magnetic field of the Earth protects us from a lot of cosmic radiation. So the sun is generating lots of energetic particles. Many of them are charged, and they're all arriving at the Earth. So what happens to them? Well, the Earth has a magnetic field around it. So I now have a charged particle coming towards the Earth from the sun. It encounters the magnetic field. What does it do? It sees a force. You now know how to work out those forces. It changes its direction. And what actually begins to happen is those particles begin to spiral. And they spiral towards one of the poles, depending if they're positively or negatively charged. And then they begin to recombine and generate light, and that's what you call the aurora, or the northern lights, that you'll see in the north and the southern hemisphere. So it's basically charged particles interacting with the Earth's magnetic field and then moving towards the poles. So you can now explain it to, if you're out with your friends tonight for dinner or something, you could explain that to them. And they'll think you're doing cool stuff at work. Okay, so if I've got a moving current, moving charge, in a magnetic field, I see a force. So we know if I consider now a wire, so I think about a thin wire, that's going to carry some current. And we're going to assume we've got positive charges flowing along this wire. So we've got some current flowing along the wire. If I take that wire now and place it in a magnetic field, and for simplicity, because I've got this QV cross B, I'm going to assume the magnetic field is at right angles to the wire, just so I can ignore the sine theta terms. Let's assume the magnetic field is coming out of the board towards you. And the way we typically draw that is a dot with a circle around it. So the dot is the top of an arrow, and the circle are where the feathers are at the back. So it's flying through the air towards you. So this is a vector coming out of the board. And you'll see the textbook and various other examples will use this symbol for the field into the board. That's the back of the arrow after you've shot it from the bow, and you see the flight spinning around. So B is coming out, current is moving along this wire. So what happens to the positive charges? They will see a force. So they will move at 90 degrees to the plane defined by the magnetic field and the wire. So the magnetic field is going that way, the wire is going that way, so it defines a plane that way. So the force is going to be to one side. So those small charges move to one side. They can't get out of the wire, so that force gets transferred to the wire, and the wire bends. So you'd actually see the wire shift shape. It'll change in a magnetic field. In this example, which direction are we? QV is going to be the same as the current. B is out of the board, so it's pointing towards you. So the force in this case is going to be in this direction. So can we estimate the size of that force? Well, if we think back to last time, we know Q is just the current times the time. We got that from defining that current is just dq by dt. If I start at 0 with 0 charge, I can say that's q, and this is t, so number of charges per second. If we think back also, I guess, to Monday, we talked about drift velocity. So drift velocity was how fast the charged particles moved through the system. Not how fast they're individually moving, but how they drifted through the system. And we argued that could be millimeters per second and was relatively slow. So we defined drift velocity. And we can say, well, that's just the current. And we defined drift velocity in terms of how long they drift over a wire of a certain length. So we could say if we knew the length of the wire, we could relate that to the drift velocity. So that's essentially our speed. That's how fast the current carrying components are moving through the wire. So we could say, well, let's consider a length of wire L. So we'll look at this particular length of wire. So we know length, so we can get the ruler out and measure that. Does that help us? Well, we can now say we know the force due to this equation must be QV cross B. So Q is just I times the length divided by the drift velocity. So let's plug that into this term. So that's going to be current times length divided by drift velocity. Oh wait, we've got a V up here. So this is also drift velocity. This is how fast the particles are moving. So this is also V drift up here cross B. So I can cancel these, which is good because that's a microscopic amount and they go away. Now I'm left with macroscopic things like current that I can measure, length I can measure, and magnetic field I can measure. So this tells me that the force on a current carrying wire is just IL, and L is the vector cross B. It's not really a sleight of hand. This term has to have a direction. So the direction is the unit vector pointing along the direction this is going. So that's going to be the same as, because I'm now confining my current to a wire, those charges have to be flowing along the wire. So the direction of current flow, or the direction of motion of the charge, has to be along L. So L has to be a vector because we know it's a cross product. So this thing has to have a direction. And we know it has to have direction because if I turn the wire so it's pointing out of the board, the force in the wire would be... It's Friday, I know, but stay with it. 5 more minutes. B is pointing this way. L would be coming out. So the angle between the two is 0. Sine of 0 is 0. So I know that the wire direction matters because if I change the direction, the force changes. So it has to have a particular direction. So I have to define the direction of current flow relative to the field. In this case, everything's at right angles, so the maximum force I get is just force equals ILB when sine theta goes to 1 and the B field is at right angles to the flow of the current. So this is useful. This is how motors work. So an electric motor and anything that you've got that's got a motor, basically you send a current through a wire. That's a moving charge in a magnetic field. It creates a force on the wire which causes the wire to move. Now maybe I put that around something circular symmetry so that causes rotation. But essentially I've got a way of converting electric field and current into motion. The inverse process is also important, and we'll talk about that later. The inverse process is if I've got a wire in a magnetic field and I move the wire, I create current. I move electrons. So we'll talk about that inductive process, I guess, next week or the week after. But essentially that's how we generate electricity. So a motor and an electrical generation system are related. But it's based on this principle, movement of a charge in a field. Anyway, Friday afternoon, so any questions? Any more lectures today? No, this is the last one, so I'm keeping you from the weekend. Okay, right, we'll stop. No, question. Pardon? Is velocity always positive? Yeah, I guess we know that the electrons are the things that are drifting, so they would drift in the other direction. But we always prefer to, because if we have to start tracking negative signs, it gets a pain. So it's easier to work with positive, so that's one good reason. If we do the same analysis again with the left hand and the electrons, we end up with the same direction for the force. So that's consistent, and that's good because that's what we measure. And I guess when they started measuring current flow in the early days, they assigned positive to one direction and negative to the other. And that was before they knew what the electron was. So at that point, current got defined as positive, and then batteries get a positive and a negative terminal, and that line persists. So most of what we do, we use a positive test charge for electric field, positive moving charge for magnetic field, which is why we've defined positive charges going this way. Now you could say, well, didn't you say last time that electrons negatively charged were drifting in this direction? Well, the same math happens. The only thing that's different is now I need to use my left hand for the force direction. but it still works out in the same sense. And that's also consistent with what we do after reading week when we start talking about currents and circuits. We use a positive current that goes from positive to negative. Okay? Okay, good weekend. See you on Monday then.